So I really apologize. The timing of our move couldn't have fallen. We're moving in the first week of school. And so I'm a little bit all over the place. And I didn't eat very much and I worked really hard this morning. So I think I'm okay, but just FYI, if I like drop, that's I think I'm fine, but I just am like, I just want to say it in case everyone's like, is she okay? Yes. And get something. Well, I ate some Pringles in my office and it's just, I don't know. We'll be okay. We're gonna get through this. It's just there's a lot. I sympathize. You guys, you have so much going on and your lives are probably feel very topsy-turvy, getting everything, all your schedules. We're all can sympathize. Let me just put it that way. I understand it's a lot. And so if you ever feel like you need somebody to unload, come and unload because I get it. I get it. Okay. So we're gonna so we want to just remind ourselves of what an atom is, because a lot of times when we are talking about this stuff, when we're talking about radiation and things like that, and when we're talking about the reaction that happens inside the tube head, it's all on a molecular level. It's all on a level of atoms and electrons and protons and neutrons. It's all happening on that level. It's micro. And so we just want to, but that's about all we really have to know, is that this is what we're dealing with. So an atom has the neutron and the proton in the center of the nucleus. That's what's in the nucleus. Our neutrons are neutral and our protons are positive. And then orbiting all around it like a little solar system is our electrons. And they orbit in various shells around the nucleus. And the electrons are negatively charged. I don't know if I said that or not. But this is not to scale, because an atom, the nucleus of an atom, is like a football in a football field. Like the nucleus is very tiny, and then the rest of it with the circulating, orbiting electrons is much bigger. So this is not to scale. The other thing I wanted to make sure that I tell you guys is that, especially today, since I'm having a bit of a day, but is that my notes are usually they're written in a way that's almost like I'm kind of trying to explain it and talk to you in the notes. And so always read the notes, because it's usually information I really want you to know. And they're in the PowerPoint there. Okay, so some vocabulary here. And I'm just, because I don't have all of this perfectly memorized, some of it I'm just going to read off of my notes. But this is some vocabulary that is helpful in thinking about atoms and matter, which is made up of bajillions of atoms. Anything in matter in the world is just made up of atoms. And so when we're thinking about all of these topics of an atom, these are some good terms that you should be familiar with. So elements are substances made up of only one type of atom. So we can, things can be mixed, but that's the periodic table is the elements. It's like just one type of atom. And so an atom consists of the nucleus, orbiting electrons. We already talked about that just briefly. Protons carry a positive charge. Neutrons, they carry no charge, so they're neutral neutrons. And think of, and then electrons are very tiny negatively charged particles that orbit. They orbit in what we call shells. Is one way of, they call it orbiting shells. The number of protons in the nucleus equals the number of electrons. So it's balanced. There's a positive and a negative charge, and it's balanced. And so that's really important, because we think about that in one term, and then we think of ionization in another term. That's when it's not balanced. There's a charge now to it. So protons and electrons, since they're oppositely charged, when they are in the same number of each, it's a stable neutral atom. And the atomic number, the number of protons in the nucleus equals the number of electrons outside the nucleus, and that's the atomic number. We don't really talk a lot about things like this, but the atomic number, the mass number, it's good to know that those different numbers affect the way an X-ray reacts, but we don't have to know the details of like the actual interaction. But there is one part later when we talk about radiopate and radiolucent and how the white part of the X-ray is white and the black part is black. That is ultimately has a lot to do with the atomic number and mass number. And so that's about as far as we need to get with that. So we don't go into much more detail, and we'll talk about that. I think that comes next week. Binding energy is a force that keeps the electron in orbit. Because of the attraction between negative and positive, there's an attraction there. And so we call it a binding energy. The closer that we get to the nucleus, the stronger the bind. And this plays a big role in how an X-ray is produced. But that's a key point, is that the electrons in the outer shells, they are not as strongly bound to the atom or in that shell as in the shells that are closer to the nucleus. They're much stronger bound to the nucleus. And so, like I said, that has a lot to do with the production of radiation. Ionization is the production of ions. So then we're going to get into this stable atom is no longer stable because we've knocked out an electron. So ionization is the production of ions due to the ejected electron. So some orbiting electron got kicked out of the atom, and that process is called ionization. The atom becomes the positive ion, and that kicked out electron becomes the negative ion. Okay. So each shell has a maximum number of electrons it can hold. And I'm trying to think if this comes into any significant play. It comes into play a little bit when we talk about the rearranging of the electrons, but it's not like you really have to memorize these valence. I think these are also called a valence, isn't that? Some of my daughter's science courses might be popping into my brain. They're the valence electron, but anyways, there's only so many electrons that each orbit will hold. So you can see there's 2 in the K shell. That's closest to the nucleus. Those are the most tightly bound to the nucleus. And that is going to play a really big role in the production of X-rays. In a moment, you'll see. Then there's 8 in the L, 18 in the M, 32, blah, blah. You don't have to know those numbers. You don't have to memorize those numbers. You're not going to be quizzed on those numbers. The energy required to remove an electron from its orbital shell must exceed the binding energy. And again, you're not going to have to memorize a whole bunch of binding energy numbers, but what you do want to know is in the notes here, and this is shown on a slide later, but down here in the notes, it says that 70 keV is the K shell. So over here, this shell closest to the nucleus, the binding energy for this one is about 70. And so that means that anything that's coming at it, i.e. some electrons flying through the tube head of your X-ray unit, has to be at least that strong to kick out this electron. So I'll say it again. So the energy required to remove an electron that's close to the nucleus needs to exceed the binding energy. So that's a pretty important concept. It's just going to be higher. Doesn't have to be like twice as much. It just has to be higher than that binding energy. Yeah.
The electron cloud that comes from the tube head then will have to disrupt number 2, the K shell ring.
Yes.
In order to knock that off, to be able to create that.
Yes, and there's a little bit more to it because there's a couple different kinds of radiation, but yes, essentially it has to knock out that electron in order to produce a radiation or an X-ray beam. So yeah, and we'll get into that in a little bit more detail here in just a second. So the other electrons that are orbiting, they can also be knocked out and they may produce some kind of radiation, but they're more loosely bound. It's a little bit weaker of a bind, and so it doesn't take quite as much energy to knock those out. And we kind of think of it as, we think of one specific concept to make one specific kind of radiation, and then there's another kind of radiation that we'll talk about that's sort of, there's more variation in it. So we kind of separate those two concepts, and we'll get there in just a second. Okay, so how are X-rays produced? So the way an X-ray is produced, and everything that I'm talking about right now, and there is an image, if you guys have already thumbed through the PowerPoint, you'll know that there's an image of the tube, the X-ray tube that's coming up. But everything that I'm talking about right now is happening inside of this little tube. It's called an X-ray tube, and it's inside the tube head that you move around to take the pictures. That's all inside. And so everything that we're discussing right now is inside this tube. You keep forgetting to shoot that in there. You're hiding behind my monitor. So just for reference, so just so that you can start to sort of visualize it, it's all happening inside of there on a, microscopic level. I don't know if it's yeah, it's microscopic, right? You can't see it with your eyes. Okay, so how are X-rays produced? When high-speed electrons are suddenly decelerated, so they're high-speed electrons, they've been dislodged from an atom. So something, and we'll talk about why, but these electrons have been dislodged, they're out there and they're available and they're moving fast towards something else. So when those electrons are sailing through the air and then they are suddenly slowed way down or come to a stop, that energy that is produced is basically produced as an X-ray, and it's converted into electromagnetic radiation or just an X-ray. So that's where, and I think actually it comes up here in a second. No, maybe this is the slide that I always use the car crash as a good example. Yeah. No, yeah. Oh, do you not see the notes? If you download the PowerPoint app or the Box app. The notes.
We did like this morning at our 7. Yeah.
No. I want you guys to see the notes. So we'll have to, I'd like you to figure out how to see them. Because they are really, I feel like there's a little extra for me. Do you see it? Does anybody else, if anybody else is having issues and you can't see the notes from the PowerPoint slides, either ask a peer or come see me and we'll try and figure it out, because I do want you to be able to see them. No, that's good. You're like, why does he keep saying no? What does she mean? Yeah, no, that's good. Oh, as a slideshow, and then you'll, oh, don't do it as a slideshow? Okay. And I know some people in other classes have, like everybody has their own system. They might have read through it or looked through it or studied it with the notes visible. And then other people like to, because with the iPads and things that you can do. You can like write all over the slide. So some people will like write on the slide and make notes, and there's just so many different ways that I've seen students, and I don't even always know what they're doing because I don't have that. So I'm like, it's cool that you can do that. I don't have that, but so there's usually more than one way to do it. Okay. But yeah, if you haven't seen the notes yet, then definitely ask someone or come see me and we'll try and figure it out. Okay, so here you can think of a car crash when something is going really, really fast and it stops and it hits something, it busts apart, right? So that's what you can kind of visualize when you're thinking of an electron. The X-ray flies off as the debris, or and you can think of like when a car hits a wall and it just busts up into a bunch of pieces, everything that flies off of that would be the X-rays. The whole process of the election. If you're reading my notes, you'll see it says election there. The whole process of the electron decelerating or stopping happens inside the tube head. So it happens inside of this little thing, very small tube, X-ray tube, and inside the bigger thing is called the tube head. This is just called the X-ray tube. It's very similar names, just slightly different. Okay, so there are 4 main concepts that you will want to you can break them down into like 4 main concepts. The first one is that you have to generate electrons. Now I want to say elections. You have to generate electrons. You need them to go very fast. They need to be moving very, very fast in a direction that you want them to go. You have to direct them. So then comes number 3, you have to focus them in the direction, because when they are created, they'll just go. And so you want to try and like get them going in one direction. And then you need to stop them. They need to be stopped. And then that will create the energy release, which is the X-ray. So those are the 4 main concepts, and then we'll break it down a little bit further. So for the generation of electrons, we have, from the wall, it's just like, electricity coming out of the wall, electrical current, it heats a part, and this is where it's like cart before the horse. Like, do I show you? And maybe every year I think this and I just don't do it. I'm like, do I teach the parts first and then the generation? Maybe I really should have done that. And maybe I think that every year, but I brought this. And I probably go through this process every year and then I forget that that's what I wanted to do. But the electricity comes in and it heats a part of the tube, and we will go into details next week more of what it is. But it heats a part of the tube called the cathode. And this is, again, I know I've said it 4 times, but I like to repeat myself. This is all inside this little glass tube inside the tube head. So it heats half of it, and then that heating generates electrons. So we have a bunch of electrons that are become suddenly available inside of this little glass tube. And then, and this is all part of just step number 1, the generation of electrons. So the electrical current, it heats the cathode, and then we have, and because it heats it up, it starts to do what we kind of call boil off, or all these little electrons will start popping off of this little metal coil inside of there. And this, I don't know if this is the right place to say it, but if you think about this little metal coil that's inside of the tube head, you don't think about it as a solid piece of metal, and you just simply think about it as like billions of atoms, then you can kind of go back to where we were talking about everything in like like in the micro topic. You can think about it as like all these little tiny electrons, that are available. And so heating up of this tungsten target, or this tungsten filament here, will boil off a bunch of available electrons. So that's what creates the first thing that we need, which is electrons. We have to have electrons available. And that's how they become available, is they get heated off of this little piece of wire inside the tube head. So the next step is those electrons that are available, they separate from what this little tiny coil of wire that we call the tungsten filament, they separate off of it. And then this whole system of the electrons boiling off of the wire is called thermionic emission. So if you have something where you can write on it or you can highlight it, I would just highlight that thermionic emission, because that is probably a quiz question or a test question, but that is the process of this little wire inside of this glass tube getting hot, and then the electrons are boiling off of it. It's called thermionic emission. So this, again, we're still in step one. This is just the electrons becoming available. This is how the electrons become available for this whole process of X-rays generated. So this process called thermionic emission, and these electrons being available, they hang around, they jump around on this coil, but they don't go far. They stay close in a cloud. So they stay close in what we call an electron cloud. So they're all just hovering around this little piece of wire that's inside of this glass tube, and they're all available for the next step, which is what we'll talk about in a minute. So it's an electron cloud is formed, and this whole process is how many electrons we have is controlled by milliamperage. It's part of the voltage, the part of the energy that's available, and it's all controlled by the milliamperage, or we call it MA. So there's two different things that control the power and like the penetrating power and the number of electrons and how strong your X-ray is. It's either milliamperage or it's kilovolts. Those are just the two energies that we talk about. But this part right here is all controlled by MA. So I would highlight that. That's an important take-home point. So here's just another image of the electron cloud. Again, it's happening over here on this side of this little glass tube. You can see inside here, there's a little coil of metal, and that's what this is here. And that basically, if you want to think about it, if you like to think about, if you can zoom out and think about yourself as a hygienist in a room and you're there with your X-ray machine, if you come in and you turn on your machine, you've instantly started this process. So the minute you walk into your room and you're like, I got to take an X-ray and then turn on my machine, voltage surges through the wires and it starts to heat up this tiny little filament. And that's all. You haven't taken an X-ray, you haven't produced X-rays, you just turned on your machine, and now your filament heated up, and now you have available electrons. So like on a macro level, that's what happens. Yeah.
So in the book, it says that milliamperage is true current. So when you push the button, then the milliamperage like pushes you out like a current of electrons coming out.
That's actually, so the other, I hope I'm not counteracting the book because that would be bad, but the milliamperage, so that what actually pushes them across or pushes them away is your kilovoltage. So that's and their MA and kVp are just the two sort of powers. I'm trying to think of the best way to say it, but the best like electrical currents that we talk about is milliamperage and kVp. Those are the only two that we talk about. So MA will create the cloud, and then kVp is what gets it going. And we will talk about that in more depth. We just haven't gotten there, but yes, that's pretty much on the same line of what we're going on. So now now zoom back down into atoms. We're thinking about atoms again. Protons, neutrons, electrons. So this little piece of wire, this little coiled wire that's inside of our tube head, like I said, just think about it. You might think about it as like just, bajillions of little atoms of tungsten. The reason I keep calling it tungsten is that's the name of the metal. So copper, gold, that, tungsten is a metal. So you could, we just don't hear about tungsten metal very often, but that's what it is. Tungsten is a metal. So we have all these we have an atom here of tungsten, and we have the nucleus in the middle, and you see we have the K shell closest, and then we have all the little shells with all the number of electrons. And then up here, you can see there's 2 electrons in the K shell, and the binding energy, remember we talked about how the binding energy is stronger the closer to the nucleus. It's specifically 69.525. You don't have to remember that specifically, but this goes back to how you have to have a greater amount of energy to knock out those electrons. So it has to be greater than 69.525. And this slide, I show this slide again when we talk about the energy, the kilovolts. But this is just to kind of remind you that even though we're kind of zooming in and out, it's like you can visually see a little piece of metal, but so that you understand the production part, we kind of zoom back in and go, we're just talking about atoms, and that's what's literally creating the X-rays. Okay, so number 2, production of high-speed electrons. So step 1, we turned on the machine. The electrons boiled off of the coil, and they're just hovering. They're in an electron cloud, and they're ready to go when we need them. So that was step 1. Step 2 now is we want them to move. We want them to move fast. And so this is going to be controlled by what we call kVp, or kilovolt peak. And it's a high voltage. So MA, you could think of MA, and I'm not an electrician. So if you're married to one, or you are one or something, I'm just trying to give something you can think of MA maybe as more like low voltage, like it's just kind of like it's there. But then kVp is like, okay, now it's like something turned up the heat and now it's going. So you can kind of, if that helps you kind of remember the process, because we want the machine's on, some energy is flowing, but it's just enough to heat up the filament and get it going. Now, for step number 2, we need high voltage to kick it off of that cloud, kick it out of that cloud, and send it over to the next step. So we have the boiled off electrons. They are sent from, and we'll learn this is part of what we learn next week. But the cathode side, where they were just all hovering, this is called the cathode side. They're going to be kicked off, and they're going to just head over to the other side over here, which is called the anode. So when we say cathode and anode, we're talking about just 2 sides of this little glass tube. So when we literally, you're the hygienist, you're about to take a X-ray, you go into the room, you turn on your machine, got the sensor in the patient's mouth, you come out and you push the button. The pushing of the button is what makes your X-rays fly over. And then the whole process happens, obviously, very quickly. But that's what triggers this number 2. You push the button. So that just kind of gives you like a reference of what part is happening when. Electrons, the electrons from the cloud, the electron cloud, they're only gonna go in one direction. They go from negative to positive. Our cathode is a negative side. Our anode is a positive side, and the electrons are going to go from negative to positive. They're going to fly across there and go from negative to positive. But in order to get them really kind of going in that direction, they have this thing called a focusing cup, and it sort of wraps around, so like it kind of wraps around the filament, like you have this little curly metal of tungsten metal where the electron cloud is, and the focusing cup kind of just is like this half circle to kind of just visually, you can think about it, it's just trying to like get them over in one direction. So it's just this little sort of rounded, you can see the picture of it here. Oh my gosh, I'm so gonna pass these out to you guys. What is this? This big one to pass along, and if more end up on one side than the other, just let me know so we can get it to the right place. And we'll also take like a little brain break here in a minute after we get through the steps. So after I do step 4.
Charges, this is like charges or how. What is that indicating? Because the confidence in a different charges.
Yeah, I think for our purposes, it really is just helping you remember that because it's 2 different charges, the negative and positive, and just gonna flow in one direction. I think it's just trying, like, it's, if they were both negative, the process wouldn't work, or if they were both positive. So I think for our purposes, it's just trying to help you understand that because they're negative, they kind of are attracted in one direction.
Okay.
I'm sure there's more to it in like,
This is like a magnet.
yeah, right? And the charge, because with a magnet, it is like one's negative and one's positive, right? And so if you put the 2 positives together, it kind of like hovers and doesn't want to touch. But when you flip it over, they attract each other. So is anyone missing one? No, everyone's got one. So let me this is, I think what I'll do is I'll go through the 4, we'll take a break, and then we'll come and just give a quick, we go over this a lot next week. Like, you'll learn all these parts next week, but I just feel like it's good to know what you're thinking about. It's good to have like a visual of some kind. Okay. So yeah, so the focusing, so someone asked like this statement here, like charges repel. I feel like there's probably more to it than, but the concept of what's happening inside of a tube head is half is negative and half is positive. And because of that relationship, you have your electrons that are attracted, the negative electrons are attracted to the positive side. Atoms are always trying to balance themselves and be neutral. And that's like, homeostasis. I don't even know if that's, but they want to be neutral. And so a negative thing will be attracted to a positive thing because it wants to become neutral. That's just kind of the way it works. And so I think this statement here, like charges repel, I think it's just trying to give you that picture that it's negative and positive, and the negative electrons are flying toward the positive side. And that is part of the process. And that's part of why the process is happening. It's because it's negative and positive. It's not too negative. It's not too positive. It's a negative and a positive. The focusing cup designed to direct the electrons to the target spot. So it's designed to help them flow in that direction. So then we have the last piece here, which is the stoppage of electrons. And on the other side, over on the anode side, which is the positive side, we have a little, mostly there's this big chunk of copper, which absorbs a lot of heat, and we'll talk more about that later. But inside is this little other kind of sheet of very, very small sheet of tungsten metal. Again, the filament's tungsten, and then we have this little embedded bit of tungsten on the opposite side. So those electrons will fly over, they'll hit that. And when they hit it, the few electrons that make it over there and hit that tungsten target will become X-rays. But a lot of what happens is just they're absorbed into that copper and heat is produced. So it's actually a very inefficient process. We only end up with one, and this is a test question, so this is good to remember, but there's only 1% that are actually X-rays that come out of this whole big long thing that I've been talking about. there's only about 1% that become X-rays, and like 99 basically percent of it becomes heat. So when those electrons fly over there, there's this little tiny target that they're trying to get to, or that we want them to get to, because that's where the actual X-rays are generated, and the rest of it's heat. Yeah.
So the thing about the electrons hit was the anode, right?
Yes, they're headed toward the anode, and the anode, we call it the anode side, and the anode is made up of this big copper stem and a little tiny piece of tungsten metal, which is, we call it the tungsten target. And I'll show it to you guys on this thing, but that's the anode side. Yeah. So, and this is a little picture of it. So any questions there before we take a break? Okay, let's take a 10-minute break. What time is it now? It's 2:04. We go to 2:50, right? Oh boy. Hope we make it. Okay. Let's take a 10-minute break here. We'll come back at 2:15 or 2:14, and then we'll start again. And I'm going to pause the recording here. Okay. So, I resumed the recording, but it doesn't pick up what's on the dot cam. So, and I'm not going to go like mega details, because this really is next week, but just so this, because I think will help kind of facilitate in the learning process, and you can make some notes. So when you're in the X-ray room and you have the thing that you're moving around that's on the arm, that big thing altogether is called like the X-ray unit. The X-ray tube head is the part that you move around. It has the BID. We'll learn more of those, and you'll have to know those parts better, but you don't have to totally memorize all that right this second. But inside of that, so this little thing is inside of it, and this is actually where it generates. So when we talk about, this is like your sort of like a wire. I mean, I don't actually know if that's really what's supposed to be, but if you can imagine, you know, like your MA voltage or your electrical, your power comes in first on this side, which is called, see the negative here? This is your cathode side. Cathode side. And we'll talk about next week how to remember the cathode and the anode, which comes first, which is negative, which is positive. Just to a brief preview, CAT, cats tend to be kind of, you know, cats are like aloof and independent, so you can think negative cats. Sorry for any cat lovers. My daughter's like a huge cat lover. I love cats. But so you kind of can, that's a trick, you know, cats are negative. Not they're really negative, but you know. And then anode is over here. Here's your positive side, and that's your anode. Am I spelling it right? Yeah, anode. So when we talk about that first step, is we need available electrons. That first step is talking about this little wire here, which is our tungsten filament, 11, TUGSTEN, tungsten filament. That's 11. And so that's where we get our electron cloud. And I'm just going to kind of make a little cloud around here and write electron cloud. And remember, we also call it thermionic emission. I'll probably misspell thermionic, but thermionic emission. I don't know if there's two S's. But that's step one. This is controlled by MA. So this is all that information that was on the slide that says 1 on it. That's your first step, is the electron cloud formation. Then this is representing, now we need high voltage to kick these electrons off of the tungsten filament and send them over to the positive anode side to hit this little target here, which is our tungsten target. So here, let's see, what did we write on the key? Oh, she crossed it out. This is an old key, so I didn't even make this key. I'm just gonna say, let's call this, let's call 14. Hold on just a sec. Let's say you could either write like the number 2, like production of high-speed electrons, or you could write high voltage created. But this is showing that we need high voltage. Sorry, that's 2 words. Looks like 1 word. High voltage or high production of high-speed electrons. Production of high-speed electrons. So that's what I feel like, that's what we should say that arrow is they're going to come off of the electron cloud, and then they're going to head over toward the anode or the positive side. This is number 3. Number 3 in the previous slides said focusing cup, and that's what this is. So number 12 is the focusing cup, and that helps the electrons go in that direction. It's part of the cathode, which is negatively charged, focusing cup. So this is just part of the cathode side. It's negatively charged. Since this is positive, these electrons are going to be attracted to moving in this direction. Number 4, slide 13, says the stoppage of these electrons. So the electrons are boiling off here. They're flying over here because of the high voltage, and they hit. So this big thing here is copper. So 15 is copper stem, and it's mostly just for heat absorption. AB. But embedded inside of this copper stem, we have this little blacker part here. This is the tungsten target. And it's hard to write it there on 14 because it's too dark. So I'm just going to draw an arrow down. So for quiz questions or test questions, both the filament and the target are made of tungsten. This is made of copper. And the focusing cup is made of something, but I don't ask the question. It starts with an M, and it's hard to say, and I don't even really recognize it from anything else. So I might say it next week, but I don't think I have any exam questions on it. But so I always just say focusing cup. Okay, so there are other things here in this diagram, but we'll probably bring it back out next week. But those are the main things that you can use to visualize to kind of help with those slides. Yeah, question. So number 4, oh wait, number 4? Oh, 14. Or wait, where's 4? Oh, step 4. Oh, I'm so sorry. Yes. Step 4 is when they reach the target. Actually, when they collide with the target. in, because that's gonna stop the electrons. So that would be step 4. Yep, so they pass over to the anode side, they hit the target, and so that's the step 4. Step 3 is the focusing cup. Yes, it's the high voltage. It's what takes to make those electrons come off of the filament and fly over to the target. Yes, 13 would involve the KVP, and I think I'm trying to remember if we talk more about it in a minute or if that comes more next week, but it does involve the KVP. Yep. Okay. So go back. So this is the picture of it. So that's this is what one looks like. You can see that looks like copper. So you know that's the anode side. Otherwise, there's not a lot that's, this isn't labeled, so it's hard to, but because we can tell this is copper, that's the anode side. So this is the negative cathode side. This is the focusing cup, and you can't see the filament, just like you can't see the target, because just the way the picture is, but the filament would be inside of the focusing cup, and the target would be embedded in the copper, but you can't really see it. And we talk more about this next week, but this whole glass tube is leaded. It's all leaded glass, which means the X-rays can't come out except for one tiny little bit of the glass that's unleaded. So they purposely, the way they create it is they make it all lead, and they just leave this one little unleaded spot, and that's the only place X-rays can escape. So, and I think we talk about that more next week, but just for sake of, if you're interested, like to think ahead. So this is all lead lined glass, or leaded glass. When they make those glass, they put lead in. I want to just show, this one's longer and the guy's kind of talking and it's kind of slow, so I'm not going to play that, but I want to see if I can play this one. It's just shows X-ray production, kind of a nice little animation. So I want to see if I can get this one to work.
This is fast twitch, an energy drink from Gatorade. 200 milligrams of caffeine, electrolytes. Some people less astute than the average X-ray student have wondered where X-rays come from. Maybe they're created by magical wizards. Maybe they're harvested from unicorns. Maybe X-rays aren't real at all. Obviously, you understand that X-rays are real, and this lesson is about the main principles of X-ray production. X-rays are real, and they have to be created in a very specific way. There's really 3 requirements of X-ray production: a source of electrons, a means of rapidly accelerating or energizing those electrons, and finally a means of rapidly decelerating or de-energizing those electrons. If any of these requirements are missing, X-rays will not be produced. In radiography, all 3 steps of X-ray production take place inside of the X-ray tube. Electrons are produced in the X-ray tube at the cathode filament. The specific process is called thermionic emission, which is the release of electrons, ions, in response to heat. And so it makes sense that it's called thermionic emission. A current running through the filament causes it to become extremely hot, so hot that electrons are actually dissociated from the metal and form an electron cloud around the filament. This is kind of like the filament in an incandescent light bulb. A current running through the light filament creates heat, which creates the light. In an X-ray tube, the filament gets so hot, it actually creates free electrons. A cloud of electrons doesn't do us much good. So what happens next? That's where the unicorns come in. Not really, but the second step of X-ray production is accelerating these electrons, which gives them extremely high kinetic energy. This is accomplished by an electric voltage that we call kilovoltage potential, or better known as KVP. The KVP creates a strong negative charge in the filament that forces the electrons across the X-ray tube. This makes sense since opposites attract. The electrons are repelled by the negatively charged cathode and attracted to the positively charged anode. The last step in X-ray production is decelerating the electrons. These highly energetic electrons
Sorry, I just heard that for the first time. I mean, I've watched this video, but it just resonated. It was just interesting how he just said when the introduction of the KVP, it creates them to be more negative. Did you catch that? I feel like I have to listen to it again. There's always, like, when you hear more than one person explain something, they always explain it differently and you pick up on something. That's why I always like adding resources, but I was like, oh, that's an interesting point I hadn't understood. Okay, sorry.
Slam into the anode of the X-ray tube, and in the process of decelerating, they actually release their energy as heat and, more importantly, as X-rays. The number of X-rays and the energy of X-rays are actually controlled by you, the technologist, using the MA and the KVP. Increasing the MA, or the tube current, increases the number of electrons produced in the X-ray tube. Increasing the number of electrons increases the number of X-ray photons. And this is the idea of intensity. The effect of KVP is slightly different. Increasing KVP, which is the tube potential, increases the energy of the electrons in the X-ray tube, and increasing the electron energy actually results in increased X-ray energy. So that makes sense. In summary, X-rays are not produced by magic or by uniforms. X-ray production requires three basic things: a source of electrons through thermionic emission, a means of accelerating those electrons, that's the KVP, and a means of decelerating the electrons, which is what happens when the electrons slam into the anode. MA is used to control the number of X-rays, and KVP is used to control the energy of those X-rays.
And the thing he said at the end there about MA and KVP is really important, but that's more, we'll talk about that more next week. So the quality and the quantity, we talk about that later. But that, I just like that video. I think it breaks it down very simply, and there's a lot of good information jam-packed into there. I lost my PowerPoint on my side, so hold on. Okay. Okay, so this says page 14 of the text has a good summary, but this is just another little drawing of exactly what we just watched in the video. We have the cathode side with the focusing cup and the filament, and then the anode side with the tungsten target. Does anybody have any questions before we go on? Like, after watching that video, did anything click, or did anything, now a question was created or anything like that? Yeah. So that's a great question. Back in the old days, you had to literally dial everything in. You had to dial in the KVP and dial in the MA. Now they're very set. However, our machines, you'll see when we spend time in the lab, you'll see that you can do either 70 or 60 KVP for three of the machines, and then the one machine that's different, you can't change it at all. And then MA is pretty much set. So the only thing you really can control is exposure time, which is how long the process happens. So that's the only, but you actually, the three of the machines, you can change between 60 and 70. And I think we just leave it on 70. We just don't change it from that. Okay. All right, so now, how much time do we have? We have like 20 minutes. Now we go into another this is another kind of tricky concept. Hopefully I don't want to, I hate rush. I'm not going to rush it. And if I have to finish up a little bit on this next week, that's fine. I don't want to rush the concepts here, but now we're going to talk about the two different processes. So we know kind of how to generate the X-rays or the radiation, the X-ray radiation, but there's different ways that it can ultimately be generated depending on the energy that's available to us. So the two processes are called Bremsstrahlung or characteristic. Bremsstrahlung is also in the textbook called like braking. And it's because of, that'll make sense in a minute, because it's the way that what the atoms are doing. So Bremsstrahlung, braking, that's one process. And then characteristic what was the did anybody read the chapter? And do you remember general? Do you remember the general?
Generally in breaking what is under.
Oh, that's all under all under Bremsstrahlung by itself. Okay, thank you. So so we usually on tests, on assessments, we call it Bremsstrahlung. But in the text, breaking or general.
Because will not be accepted.
If you wrote the answer and you got the whole thing, the whole system right, and you wrote it down, I would be like, oh, great. But on a multiple choice question, the only options will be Bremsstrahlung or characteristic. So those are the ones I'll use on assessments. Okay. And they're the two different types of radiation. So Bremsstrahlung radiation. So now we're going to go zoom back down into the world of atoms. And so when this type of radiation is being created, and this is happening over on that, just for FYI, this is happening over on the anode side with the tungsten target. So that's where this is happening. This is the actual creation of the X-ray. So Bremsstrahlung radiation is when we call it a bombarding electron. See down here, it says down here at the bottom, bombarding. And that's because that's flying over from the tungsten filament, right? It's flying over there. So it's the bombarding electron. And it comes into contact with the target. But now we're just talking about one atom. So it's coming, one atom of that tungsten target. So it comes flying over and it starts to interact with this electron starts to interact with this atom. And what happens is it flies in and it gets really close to the nucleus. It doesn't actually collide with any other electrons or the nucleus. It just veers, it turns. And don't ask me exactly why that happens, because we don't really need to know, but it just happens. And when it happens, that action of it turning close to the nucleus creates the radiation. So a couple interesting things about it is because it will come in at different angles, different variable, right? It's not always going to come into the same place. It might come in maybe a little farther away or a little closer, but because this bombarding electron, this one little negative ion comes flying in very variable spots, the type of radiation varies. Some are weak wavelengths, some are strong wavelengths. They're all different types of frequencies and wavelengths. And so that's the biggest, let's see, what do my notes say? Let's see, so many different energies, wavelengths. Okay, well, I guess we talk about it more later. But that's a big thing. When it comes to Bremsstrahlung, what you want to know is it's coming in, it's changing its course, it's changing direction, and it's going to produce many different types, many different wavelengths of radiation. Those are your big take-home points for Bremsstrahlung. Characteristic is totally different because you take this bombarding electron that's flying across, coming over to the tungsten target, and what it does is when this process happens, it comes in and it collides with another electron in the K shell. So it has to specifically be coming into contact with an electron in the K shell. That's the shell closest to the nucleus, and it has the strongest binding energy. But, well, no, I don't want to jump ahead of myself. So anyways, it knocks that electron out, and that electron gets knocked out of the atom, and then everything has to rearrange because the atom wants to create like a neutral position. So all the electrons and all the other orbiting balances move up because there has to be 2 electrons in the K shell. That's how the atom is. It's like, I must have 2, and then the next one must have 8. And so because it wants to create that environment where it's stable, all the electrons move up. And when that happens, that whole process happens, it creates a radiation. It releases energy, and that energy is the X-ray. And so the big difference here is because it's always hitting a K shell electron, you're always getting the exact kind of radiation. So those are your big differences. Bremsstrahlung, it comes in, goes off different ways. So you get different wavelengths, you get different penetrating powers, but with characteristic, it's always going to hit this one tightly bound electron in the K shell, so it's consistent. So those are some things to help you to remember. Characteristic is consistent. Oh, that's a good one. So that's something, it's always the same. Bremsstrahlung is variable. Okay, and then, so here's that same slide from a little while ago. You have to have, you can't have a unit set at 60 kVp and expect to be making characteristic X-rays or characteristic radiation. You just, there's no way, because you don't have the power to knock out an electron in the K shell.
So I know that there are two different ones.
Mm-hmm.
So the KVP, we can choose that then as the provider. What kind of radiation we're getting?
We actually, well, so it used to be really easy because we've upgraded a lot of our units in the past 5 years. So when I first started, we had all these units that were just set to 70. So it was just easy. We'd be like, in our clinic, we only make characteristic radiation. So it was a kind of a nice way to remember that, because you had no control over it. But now we do have units that you can actually turn it to 60. So, but we leave it at 70. So when we're there in lab next week, we'll show you the button where you can actually change it to 60. In the end, you're still going to get an X-ray. It's not going to hurt your patient. You're not, like, nothing really significant happens, other than I actually think your consistency and the image quality probably is better on 70. 60 might be meant for, like, maybe kids or something, because it's a lower, I'm really not, we don't really change it. Long story short, we don't really change it. Yeah. Mm-hmm. And then we have one unit that's a different brand, and I'm like 99% positive that one is set at 70. So really, I can still say in our clinic, we make characteristic radiation, but we do have the ability to change. I'm not sure who it was. It you guys? You're both.
So just to make clear of that, so then it has to be at 70 so that we can disturb the electron on the K shell.
Yes. Yep. So it has to, the power in the KVP, the energy has to exceed the binding energy of the electron in the K shell. And so your KVP has to be 70, because the binding energy there is 69.525. So when we have the machine set to 70, we know it's powerful enough to knock out the electron in the K shell. Yeah. Oh, Lolly, yeah.
So when we're taking an X-ray, how is this sort of monitored, which process gets chosen, or do they happen at the same time?
So we have, all of our machines are currently, unless someone pushes one of the buttons, and we'll show you in lab next week, but really I don't think anyone will. There is a place where you can push it to 60, but if everyone just leaves the machines the way they are, they make characteristic radiation. So I don't think we actually, and someone last year asked a really good question, and I wish I had dug into it more, but the weeks go by so fast and we're like, more material. But someone's like, well, can you make Bremsstrahlung and characteristic at the same time? I was like, oh my God. Why would you ask that? It's a good question, but I don't know. And you absolutely cannot make characteristic below 70, but can you make Bremsstrahlung at 70? You don't need to know that for a test. So if someone wants to dig into that and tell me the answer, that'd be great, but you're not tested on that. But yeah, so we're making characteristic in our clinic.
So depending on what energy is, if it's above the binding energy, then it's below, then it's the breath.
Yes, if it's above the binding energy of a K shell, then it's characteristic. And if it's below that, then it's bremstrolon.
So then, when you said that the bremstrolon was the most common, and for us, the characteristic is the most common?
Yeah, and that might be, well, so that's another very good question, actually. That's from the textbook. And so I'm always like, well, I guess it's the most common, but it doesn't make sense because a lot of these are fixed. Like a lot of them are fixed. And so that's another, I'm actually going to write that down because that comes up every single year. People say, what you say is the most common. So I think that one thing that can be confusing is that a lot of X-ray is made that never comes out of the machine. It gets absorbed, it's lower penetrating power, it gets absorbed into like the lead of the glass. And so it could be that some of that is created, but it's not part of the useful beam. It's not part of what we actually use to make the actual picture of the person's teeth, that we're taking. So when they say it's most common, it could be that within the machine it's being created, but it's not what we're using to get our picture. Yeah. Yes, yeah, like we call it a useful beam, and that term will come up in a little bit, but it's what literally at the end of this whole thing comes out of the machine, comes toward the patient and exposes the X-ray or exposes. And so that could be what that means. And every year that comes up because it's in the notes and it says it's the most common, but we use characteristic but I think that that's what it's referring to really, is that there's lots of different radiation or X-rays that gets created, but they're not all useful or used. But I'm gonna research that. Okay, you guys, I love the questions. Now I want to read my note here because I just saw it says something about 65. Maybe? Yeah, let me see. It could be an old note. Because a lot of those machines are new. Let me see. If you'll notice, 70 kVp, and you may remember that I said earlier that our machines in our levers. Oh, okay. If you can see the notes for slide 20, just draw a big line through all that. I think it's because we recently got 2 new machines, and this note is this is my 4th year teaching. And so some of these notes may be a couple years old. So where it says, I said earlier, our machines and the rad lab are set at 65 kVp. So do you think we create characteristic? You can just put an X through that. We do create characteristic radiation in our lab. That's what we create.
Runs too long? With the note, because I was like, the only set at 65, but don't think it. So is a 70 issue?
I think this because the older machines, well, maybe our older machines were below. Maybe that is what it's irrelevant. That's why I say cross out the note, because we've gotten new machines and our new machines are set at 70, but maybe our older machines that we had a couple years ago, maybe they were set at 65. And if they were set at 65, I hope I'm not making this more confusing. If that was true, then we didn't used to make characteristic, we used to make bremstrolon, because you have to be at 70 kVp in order to be making characteristic. But if anybody sees that note, I'll just cross it out. I'll edit it too. I'm going to edit slide 20 and I'll edit that note. But basically the take home point is, if your machine is not set at 70, if it's below 70, you're not making characteristic radiation, you're making bremstrolon radiation. That's the big take home point for that.
And then within the characteristic radiation, the electron that is sent off, that creates ionization. And is that why the KVP will be stronger than if it comes out?
gosh, that's a good question. It's stronger because of where it's affecting one of the strongest binding electrons. And then it's consistent because it's always hitting that same electron in that same shell, which is the most strongly bound one. And so what's coming off of that, or the result of that, is going to be like a more consistent. And remember in the video, it said MA kind of is involved with like quantity, like how many electrons. But KVP, the higher your KVP, it's like energy, so higher energy, more power. And so because we're dealing with a 70 KVP, it's more powerful. So it's going to create a more powerful radiation or X-ray. I hope that answered the question. Okay, particulate radiation. Good news is we don't need to know very much about particulate. I'm sure there's a ton to know, and we're not going to learn details about particulate radiation. X-rays are electromagnetic radiation. And so there is a test question that asks like the difference, and the take home point, highlight this: particulate radiation, they're tiny particles of matter, and they possess mass, and they do contain a charge. So particulate radiation, all we really need to know, there's a little bit more information in the textbook. You can, to get a little bit more of a rounder sort of understanding, you can read a little bit more, but they contain mass and they have a charge. Electromagnetic radiation is different, and it does not have mass. And so when we talk about the difference, if there's a test question that says which one has mass and charge, the correct answer is going to be particulate. And that's really that's as far as we're going to go. Because we're talking about X-ray production, and we're talking about X-rays. We're not talking about particulate, but particulate radiation is like the cathode ray that Röntgen was working with, but what was flying off of that happened to be X-rays, and so that's part of that story from the history of it. But so that's where particulate radiation comes into play. It's they're all invisible rays. But we're studying electromagnetic radiation. So
just to clarify,
yes,
particulate does not have a charge, or it does create it?
It does have a charge. Let's go back. Sorry, let me go back. I know there's a little bit of information on this slide, and I kind of just went over it. So what you would highlight here is particulate. You can highlight particulate. It possesses mass, and it does contain a charge. Do contain charge is very poorly written. So, and then see down here, like technically the neutron of a particulate says mass and no charge. Just don't ignore it. I mean, there are facts about this science that are true, but it's not what we're focused on. So to make things easier so that you don't need to remember even more details than you already have, I'm just summarizing it as particulate has mass and charge. And that's literally all I'm going to make you need to know. Yeah.
Is all of this information going to be like on the board again?
Yes. So everything with the board, and it's going to feel like a lifetime ago when you go to take your board, but yes, it is. And but every board is like different, so everybody has a different exam and a different number. So one person might have 20 radiology questions, and you might have a question specifically about the cathode and the anode. Like it might ask, but that might be like one question out of 400 questions. So it's not like, it's like do or die, but yes, everything is up for grabs, and everyone will have a different, some people have more oral medicine or like pharmacology questions. Someone might have more, something else. So it's all, but yes, definitely radiology is absolutely, and they usually do ask a fair amount of these types of questions. Okay. Is it over? Do I have to stop? I'm so mad at myself. Did I go over? I went over. I'm sorry, you guys. I will pick up here on Thursday and, just like, remember I said the quiz is over this PowerPoint, but I'll make sure there's no questions after slide 22 and the bite wings. So the bite wing slides that from the, introduction to radiology, that material and what I covered today will be on the quiz on Thursday. Okay. Okay. Thank you guys.
Well, we have to do any like kind of thinking or lesson on this one.
No, if you do, it would probably be, I can't remember. But it would probably be something that would be very obvious and easy. It wouldn't be tricky.
Do you have any like practice things on?
There is, if you noodle, and I'll open up week 2 if it's not already open this week, but there are examples for practice.
Multiple choice.
Multiple choice.
It's all fine.
I think it's gonna be on it.
Yeah, that's my.
Thank you for this.
Of course.
I feel much better.
Oh, good.
Feeling better. Yes. I was like, oh, good. This is the first time I'm gonna faint in front of a class. I didn't feel like I was gonna faint. I just felt shaky and not well. I know.